Mr. Ram, for your kind introduction. And also, I would like to express my sincere gratitude to the Press and also TNQ for inviting me to India and also for giving me this great opportunity. I started my career as a surgeon, but I now don't see any patients. I had two reasons to quit surgery. The first reason was that I was not so good at surgery. The second reason was that I found even a very good surgeon cannot help many patients suffering from various diseases and injuries. For example, for patients like Christopher Reeve, who suffered from spinal cord injury. Once this happened, we cannot do anything for these patients. Also, these patients, like Lou Gehrig, suffering from amyotrophic lateral sclerosis, ALS, also known as Lou Gehrig disease in the States. Lou Gehrig was a great baseball player long time ago, more than 70 years ago. He played very well in 1936 and 37, but in 1938, he became unable to play well. And in the following year, he was diagnosed as ALS. He had to retire. Then he passed away in 1941 when he was only 37 years old. Because of this tragedy, this disease is known as Lou Gehrig disease. This happened a long time ago, more than 17 years ago. However, we still don't have a good medicine or a good treatment for these patients. ALS is also known as motor neuron disease. In these patients, for unknown reason, their motor neurons specifically get degenerated and eventually die. Because of this, these patients cannot move, cannot speak, and in the end, they cannot breathe. So without help of respirator, these patients cannot survive. However, these patients can still think, they can still see, they can still listen. So this is very difficult disease, not only for patients, but also for their family member. Again, we still don't have any effective treatment, primarily because we do not have good disease model to understand the disease mechanisms and also to search for effective drugs. Well, we do have mouse and rat models of ALS. A few chemicals, drugs, have been identified effective on those animals. However, those chemicals are not effective at all on human patients. So for ALS, animal models are not good. We have to use human cells, human motor neurons. However, it is very difficult to obtain motor neurons from patients. If we can perform biopsy, and if we can get a small amount of motor neurons from patients, their motor neurons are already degenerated and many of them are already dead. So it's very difficult. And motor neurons cannot proliferate, cannot divide at all. So we cannot increase the number of motor neurons. So it's not sufficient. Usually the amount we can obtain from patients is not sufficient to perform many experiments and to perform drug screening. Because of these two reasons, because I was not so good at surgery, and because many diseases and injuries cannot be treated even by good surgeons, I decided to change my career from surgery to a basic scientist. I thought only basic medical science can help these patients in the future. So I decided to go back to graduate school. I got my PhD in Osaka, Japan. And I decided to continue my training as a scientist in the States, in San Francisco. I did my postdoc training at Gladstone Institute of Cardiovascular Disease in San Francisco between 93 to 97. At that time, the director of the institute was Dr. Robert Mady. I learned many things during my postdoc training, but probably the most important thing I learned is VW. One day, Dr. Mady taught us postdocs how to succeed as a scientist. And he mentioned, you have to have VW. Well, he had, and he still has Volkswagen, VW. At that time, and I still have Toyota. So I thought, well, I'm not in a good position. But Dr. Mady said, in this case, VW does not mean Volkswagen. VW means vision and work hard. So it's very easy to say, but it is very difficult to have good vision and to work hard. So I still keep this simple word, VW, in my mind always. This is a picture taken in 1995, a picture of myself and of my mentor, Dr. Tom Inerarity. So it was approximately 17 years ago. The purpose of this slide is to show you that I used to have more hairs. That's the only one purpose. So in addition to VW, I met very important thing. Actually, I met a very important cell during my postdoc training, which is embryonic stem cell, ES cell. As many of you know, ES cells are derived from embryos, very early stage of embryos. ES cells were first generated from mouse embryos in 1981 by Dr. Martin Evans and also Dr. Gail Martin. Embryonic stem cells have two very special, very important properties. The first one is their rapid proliferation. And the second property is their pluripotency. Pluripotency is the ability to differentiate into many different types of cells, somatic cells and germ cells. So at least in theory, from embryonic stem cells, we can make virtually all types of cells, more than 200 types of cells that exist in animal body. After expanding ES cells, we can make many types of somatic and germ cells. Because of these two very important and interesting properties of ES cells, I got very, very interested in how mouse ES cells can maintain these very special properties for a long time, for more than weeks or months or even years. In 1997, I went back to Japan and I decided to continue my research on mouse embryonic stem cells. However, soon after I went back to Japan, I got sick. The name of my disease is or was PAD. This disease is not in any medical textbook because I named this disease by myself. So it has not been approved in any countries. But PAD stands for Post-American Depression. There were many reasons for my PAD. First of all, nobody around me understood what I was working on. I was working on mouse embryonic stem cells. I was able to identify a very important gene which plays very, very important essential roles in mouse embryonic stem cells. However, I was in a medical school and most of my colleagues were physicians. And I was often told, I was often advised by my colleagues like this way, Shinya, you should stop working on that strange mouse cell. You should do something more related to human, more related to medicine. That was one reason for my PhD. It was, very difficult to have nobody to appreciate my research around me. The other reason, another reason was that 20 years ago, the scientific environment in Japan was not as good as that in the States, in many places. In some places, it was very good, but at least in my place, it was not as good. So my PhD became became very bad, worse and worse day by day. And I was about to quit from science. I was about to go back to clinics, although I was a bad surgeon, but I thought I could still help some patients by going back to hospital. However, very luckily, two events happened which rescued me from PAD. The first event was the generation of human ES cells, human embryonic stem cells, by Dr. Jamie Thomson in 1998. He was able to generate embryonic stem cells from human embryos, which have the two same important properties as mouse ES cells. So we can expand human ES cells as much as we want. Then we can make many types of human somatic cells in a large amount from human ES cells. Because of those two properties, many scientists and physicians began to think that human ES cells may be able to help patients by applying to regenerative medicine. As you can see in this slide, at least in theory, from human ES cells, we can prepare many types of human somatic cells in a good amount. For example, dopaminergic neurons, neural stem cells, cardiac myocytes, pancreatic beta cells, insulin-producing cells, and so on. Then, by transplanting these human cells into patients, we should be able to help treat patients suffering from various diseases and injuries, including Parkinson's disease, spinal cord injury, cardiac failure, diabetics, and so on. So it turned out that ES cells themselves are very, very related to human disease, human medicine. So I realized that I didn't have to change my research target. I can continue working on embryonic stem cells. So that was the first reason, first event which rescued me from PAD. The second reason was my promotion to another institute. Oh, I'm sorry, going to the second reason. The first reason was human ES cells. However, human ES cells face many challenges. For example, we cannot make human ES cells from patients' own cells. So that means if we use human ES cells in transplantation, in cell therapy, we have to fight against immune rejection. More importantly, in order to generate human ES cells, we have to destroy human embryos. Many people are still against the usage of human embryos in any form. Back in 1998, in Japan and in many other countries, we were not allowed to use human embryos in research. The second reason, second event which rescued me from PAD was my promotion to another institute in Nara Institute of Science and Technology. I was recruited as an associate professor, and I got my own laboratory for the first time in my life. As you can see, this institute has a beautiful campus. They have many good faculty members. They have many good scientists. They have good scientific funding. And more importantly, they have many good graduate students. So because of this new, much better scientific environment, and also because of the generation of human ES cells, I was able to overcome PAD, and I was able to continue my research, basic research. Then, after moving to this institute, I had a difficult task to recruit students. Every year, approximately 120 graduate students enter this institute. And there are approximately 20 laboratories in this institute. So every year, there is a competition among 20 students for those 120, among 20 laboratories for 120 students. Students have the choice. We do not have any choice. So I was not sure at all whether I can attract any students, because I was the youngest PI. I was the least famous PI. I was the poorest PI. So I was not sure if any students would join to my laboratory. This is a graduate school. So if I had no students, I would have been in big trouble. So I thought what I could do to attract students. Then BW came into my mind again. I thought, well, it is very difficult for me to have good funding, to have sell paper, to become famous. It's impossible. However, I should be able to have a good vision to attract new students. Based on that idea, I thought very hard to have a clear vision of my own laboratory, and then I made this as a long-term goal or a vision of my own laboratory to make ES-like stem cells, not from embryos, but from somatic cells like skin fibroblasts. If we can do this, we can overcome many challenges that human embryonic stem cells face. This was right after the birth of Dory the sheep. Dory was born by somatic cloning. Dory was born from a somatic cell. So from that success, we knew that we should be able to reprogram somatic cells back into the embryonic state. We just didn't know how to make it. So in year 2000, I had an opportunity to introduce my own research goal, my vision, to 120 students. All PI had such an opportunity. I used almost the same slide as this to introduce my goal, my vision. I knew this is very difficult. This would take 20 years, 30 years, or longer, maybe forever. I knew that, but I didn't tell that to students at all. I just told them how wonderful it would be if we could make this. That strategy worked, and I was able to recruit these 3 students. So these are my very first students, Kazu, Eiko, and Yoshimi. This picture was taken 2 years later when they received their master degree. After obtaining master degree, Kazu and Yoshimi decided to continue their graduate work in my laboratory. Kazu is still with me. So I had a clear vision to make ES-like cells from somatic cells. And thanks to these new students, and also thanks to some other lab member, we were able to work very hard. And very luckily, it didn't take 20 or 30 years. It took 6 years before we became able to achieve our initial goal. In 2006, we were able to publish this result in Cell, thanks to Emily. She was already the chief editor of Cell at the time. So in 2006, we were able to show that by introducing these 4 transcription factors, OCT4, SOX2, CMYC, and KLL4, into mouse fibroblasts, mouse skin cells, we can actually generate ES-like stem cells from mouse skin cells. So we designated these new type of stem cells iPS cells, induced pluripotent stem cells. In the following year, 2007, we and others were able to recapturate the same strategy, same reprogramming in human skin fibroblasts. So I want to show this slide. I often have this opportunity, this kind of opportunity to introduce about iPS cells. However, it was not myself, who generated iPS cells. It was mainly these three young scientists who generated iPS cells. Yoshimi and Kazutoshi were my very first students. Tomoko was my first technician. So I was, without these three young scientists, we could have never generated iPS cells, at least in my own laboratory. I'm very, very grateful to these three young scientists. So after we publish the cell paper, human iPS cell generation in 2007, Kyoto University has decided to open a new center for iPS cell research and application. We moved to this new building in 2011, last year. We now have more than 300 people working in this building. I also have a small group, small laboratory in San Francisco at Gladstone Institute. I have 4 postdocs, so it's a very small group. But last December, Gladstone obtained a good amount of money from Roddenberry family. And thanks to their help, we now have a new stem cell center, Roddenberry Stem Cell Center at Gladstone. Mr. Roddenberry is the person who developed this famous Star movie, Star Trek. So thanks to Star Trek, Gladstone now has a stem cell center. So in these 2 stem cell institutes in Kyoto and also in San Francisco, we have been generating iPS cells from many patients, and also from healthy healthy donors. This is how we make iPS cells. All we need is a small medical procedure, skin biopsy. It takes only 5 minutes. We can take a small amount, 2 or 3 millimeters of skin fragment from patients. From these skin fragments, we can generate skin fibroblasts. By introducing those 4 factors which I showed in the previous slide, we can convert these skin fibroblasts into a completely different type of cells, namely iPS cells. iPS cells are indistinguishable from human ES cells in morphology. And once they become iPS cells, we can expand iPS cells as much as we want. And after expanding iPS cells in the undifferentiated state, we can then make many types of human somatic cells from these iPS cells. For example, we can make this kind of beating cardiac myocytes from human iPS cells. These beating cardiac myocytes used to be just skin cells only a few months ago. So every time we see this beating cardiac myocytes from iPS cells, we still feel very strange. This is why we are making iPS cells from many patients. Again, by using iPS cells, by establishing iPS cells from patients, we can expand iPS cells as much as we want. Then we can make many types of somatic cells, including neural cells, cardiac myocytes, hepatocytes, and beta cells, having the same genetic information with the patient. So basically, these somatic cells are patients' own cells. Then we should be able to use these cells in both in vitro and also in vivo. In vitro usage will be includes toxicology testing, disease modeling, and drug screening. In vivo usage includes cell therapy, cell transplantation therapy. So let me give you one example for each application. So let me begin with disease modeling and drug screening. So again, I want to discuss about this disease, ALS. This is another patient. This is a very famous Japanese professor. When I was a child, he was also known as a very popular TV personality in a quiz program. However, he is now suffering from ALS. He can hardly speak, so he has to communicate with his wife by writing. But this picture was taken a few years ago. Now he cannot even write. Again, we still don't have good treatment, good medicine for these patients because we cannot obtain enough amounts of motor neurons to perform drug screening, to understand disease mechanisms. However, now that we have this technology, iPS cell technology, many scientists in the world have been generating iPS cells from patients' own cells, from patients suffering from ALS. Again, we can expand these patient-derived iPS cells as much as we want. Then we can make motor neurons from iPS cells. Motor neurons cannot proliferate. Motor neurons cannot divide. So we cannot expand motor neurons. However, we can expand iPS cells as much as we want. After expansion, we can make motor neurons in a large amount. These motor neurons, again, have the same genetic information with ALS patients. So now many scientists in the world are trying to utilize these motor neurons, which they generate from patient iPS cells in understanding disease mechanisms and also in screening effective drugs. In our own institute in Kyoto, in Saira, Dr. Haruhisa Inoue, who is also a neuro physician, who have many ALS patients in his clinic. He has generated iPS cells from many ALS patients and also from control individuals. He has successfully generated motor neurons from those iPS cells, and also he has successfully purified motor neurons from iPS cells. As soon as he purified motor neurons, he noticed that the morphology of ALS patient motor neurons is abnormal. Motor neurons have long so-called neurites. In our real body, sometimes motor neurons have neurites, which is more than up to 1 meter from brain to muscle. In Petri dish, it's shorter than 1 meter, but usually they have multiple neurites, which you can see here. From cell body, they have multiple neurites. But Dr. Inoue noticed that ALS patients, their motor neurons, which he generated through iPS cells, have significantly shorter neurites, as you can see here. The neurites are much shorter. So he is now using this as an assay system to screen many drug candidates, many chemicals. We are hoping that in the near future, we will identify chemicals which can revert this abnormal morphology back into normal morphology. And we are hoping that some of those drug candidates turns out to be effective on human patients. So we have set up this kind of drug screening system, robotic system in our institute in Kyoto. We have obtained more than 50,000 chemical compounds, drug candidates. So we really hope that we can identify some of those drug candidates is effective on human ALS patients. Let me move on to the second application, which is toxicology or side effect. Many medicine, many drugs have various side effects in hearts, in liver, and in other tissues and organs. Many medicine, including antibiotics, have this kind of cardiac toxicity, so-called long QT syndrome. Long QT syndrome often leads to this kind of lethal arrhythmia. We really have to predict this kind of cardiac toxicity, cardiac side effect, as early as possible in drug development. Probably the best way to predict cardiac side effect, cardiac toxicity, is to apply drug candidates directly on patients, directly on volunteers, and monitor their EKG. However, this can be very dangerous. If the drug candidate has severe cardiac toxicity, which may cause lethal arrhythmia in these individuals. So from an ethical point of view, we cannot perform this kind of test. However, now that we have iPS cell technology, we don't have to ask this kind of very dangerous test. Instead, we can just ask a skin biopsy, or we can now generate iPS cells from peripheral blood samples. So all we have to ask is to take some blood samples from volunteers. Then we can make iPS cells. From iPS cells, we can make beating cardiac myocytes, just like I showed in the previous slide. Then we can make a record of kind of EKG in Petri dish. Then we can apply drug candidates onto the beating cardiac myocytes in Petri dish. We can test any concentrations. We can test very, very high concentrations. As a matter of fact, at least 2 companies in the world already have started selling human cardiac myocytes derived from iPS cells. So one company is in the States, Cellular Dynamics International, also known as CDI. Another company, the other company is Riprocell, which is a Japanese company. So both of these companies have a product. One company has iCell, the other company has Q-Tempo, which is human cardiac myocytes derived from human iPS cells. So I know that many pharmaceutical companies have purchased these human cardiac myocytes, and they are now trying to use this system in their drug discovery program. So this application is just around the corner. Let me move on to the third application of this technology, which is cell therapy. We have in Japan, we have a collaboration with another university, with Keio University, Dr. Hideyuki Okano. This is what we would like to achieve in the very near future. We would like to treat patients suffering from a spinal cord injury by transplanting neural stem cells derived from human iPS cells. We have been testing this strategy in animal models. So this is a result of a mouse model. We generated a spinal cord injury model at a thoracic level in mouse. So without any treatment, this mouse cannot move his or her lower extremities. However, by transplanting neural stem cells derived from iPS cells, the mouse showed a significant recovery, just like this. We have obtained a very similar promising result from a monkey model. We have been using a small monkey known as marmoset. So we have the same strategy is also effective in monkey model. So we are hoping that in the near future, in 2 or 3 years, we can start clinical studies using with real human patients suffering from spinal cord injuries. So if we use iPS cells from each patient-specific iPS cells, we should be able to overcome these issues, ESCO issue and immune rejection, which human ES cells are facing. So this is very good. However, at the same time, making iPS cells from each individual would cost a lot. We estimate that it would cost up to $1 million to make and to apply iPS cell technology from if we make iPS cells from each patient. It's too much, too expensive. And also, it will take very long to make iPS cells and to expand and to induce differentiation into like neural stem cells. It takes at least 2 months to generate iPS cells. It takes another 1 or 2 months to expand iPS cells. It takes 2 or 3 months to induce differentiation into neural stem cells. So in total, it takes at least 6 months. However, in the case of spinal cord injuries, Dr. Okano and others have shown that the best result can be obtained if we transplant neural stem cells within 4 weeks after the onset of iPS cells. So if we start making iPS cells from patients, we can never make it because we only have 4 weeks, but it takes at least 6 months. So how can we overcome this issue, time and money issue? Well, one way to overcome this issue is to make iPS cell bank. So instead of making iPS cells from each patient, we are planning to make iPS cells in advance. So that means not from patients, but from healthy volunteers. We have found that peripheral blood and skin fibroblasts can be good sources for iPS cells. In addition to these cell types, we have shown that cord blood cells can be a good origin of iPS cells. In many countries, we have already established cord blood bank. So if we can collaborate with those existing cord blood bank, it's very effective to promote this idea. We have also established integration-free method, safer method to generate iPS cells. And also we are now trying to set a rigorous quality control system to select the best, safest iPS cell clones. I hope we can finish these preparation within a year or 2. Then we can start producing iPS cells suitable for regenerative medicine. We have set up this kind of cell processing facility for iPS cell therapy, FIT, in our institute in Kyoto. So we're hoping that in the very near future, we can start making iPS cells at GMP level in this clean facility. So in my talk today, I hope I was able to introduce these 3 major applications of this new technology, iPS cell technology. Disease modeling, drug screening, toxicology testing, and cell therapy. However, this technology is still very new. It is less than 5 years old. So the technology still faces many challenges. For example, we still don't know whether iPS cells can really replace ES cells. In another word, we're still testing whether iPS cells are equivalent, indistinguishable from ES cells. This is probably one of the most important questions we have to ask, we have to answer. Also, when if we perform cell transplantation therapy, we have to double check that those iPS cells are safe. We don't want to see any side effect, especially any tumor formation after transplanting like neural stem cells derived from iPS cells into patients. This is also very important issue. In addition, we still have to perform many basic researches to induce in vitro differentiation. It is relatively easy to make cardiac myocytes and neural stem cells from iPS cells and ES cells. However, it is still very difficult to generate hepatocytes and beta cells, pancreatic beta cells from iPS or ES cells. So we still need much more basic research efforts. Also, for some diseases, it may be very difficult to recapitulate, to make disease models in vitro. So we still need a lot more basic research to establish disease models for many diseases. So again, there are many challenges we have to overcome before we can apply this technology to medicine, to bedsides. However, I'm very optimistic because now many scientists are studying iPS cells. This world map shows the location of stem cell centers in the world. This was drawn a few years ago, so we should have much more right now. We have some in Japan, some in India, many in Europe, many in the States. In most of these stem cell institutes, scientists are studying iPS cells. I have in addition to Kyoto, I have a small group in San Francisco. So I visit San Francisco every 5 or 6 weeks. When I went to San Francisco a few months ago, I found this car, which is not my own car, somebody else's car. This is just a Mini Cooper, but look at the number plate. It says iPS cell. So I was very surprised. This suggests that many researchers are working very actively on this new technology, iPS cell technology. So I'm very optimistic that because of these efforts by many scientists, we can overcome many challenges that iPS cells are facing in the very near future, and we can contribute to the new treatment of many intractable diseases in the near future. So finally, I would like to thank many of my colleagues and fellows and students, both in Kyoto. We have more than 300 people in this building. This is only part of them. In San Francisco, I have a small but very good group of people, these people. I'm very, very grateful to all of these people for their efforts. This is the very last slide. In this June, we are going to have this meeting, the 10th annual meeting, anniversary meeting of ISSCR, International Society for Stem Cell Research, which is now the biggest stem cell society, stem cell meeting in the world. Every year, more than 40,000 scientists gather in this meeting. This year, this will be in Yokohama, in Japan. So I hope I will meet many of you in Yokohama in June. With this, I'd like to finish my talk today. Thank you so much for your kind attention. Thank you very much.